Stoke Space started with a test vehicle so odd it was easy to write off as a miniature Starhopper Echo. But today, at Moses Lake, the company is no longer showing a curiosity. It is stacking real Nova hardware for a fully reusable two-stage rocket. The question now is whether Nova is a serious challenger or just another startup pulled along by SpaceX's momentum. Its answer depends on hardware: a reusable booster, a radical upper stage with an actively cooled heat shield, and a first flight target that could move Stoke from footnote to threat much faster than its size suggests. Stoke's newest milestone was not a launch, and it was not a full booster firing. It was the first Nova first-stage flight hardware leaving the factory, arriving at Moses Lake, being stood vertical, and surviving a 3-week proto-qualification campaign in early June 2026. That wording matters. The company was checking whether real booster hardware, built close to flight configuration, could survive the loads, interfaces, procedures, and failure paths it will face before anyone commits it to flight. The verified test scope was unusually broad. Stoke listed 46 structural objectives for the first stage, covering how the vehicle behaves when it is lifted, supported, pressurized, restrained, and loaded through ground test conditions. Those are the unglamorous cases that can decide whether a rocket is safe to fuel, safe to transport, and safe to fire. The campaign also went beyond the metal structure. Stoke tested fluid systems, avionics, software, ground systems, and operations procedures around the stage. That means the team was not only measuring tanks and load paths. They were practicing how Nova talks to the pad, how commands move through the vehicle, how the ground crew works around it, and how the whole system behaves as one machine. And Moses Lake gave them more than a clean checklist. During the campaign, the stage endured hurricane-force winds and a severe lightning storm while standing vertical. That turns the test from a simple fit check into a real environmental stress case. For a reusable booster, surviving the test site matters because launch hardware spends a lot of time exposed before it ever leaves the ground. So the headline is not that Stoke suddenly proved Nova can reach orbit. It did not. The real achievement is narrower, but important. The first stage hardware made it through a broad proto-qualification campaign without the company announcing a major setback. That raises the question at the center of this milestone. If the rocket has not flown yet, why does a structural test matter so much? Nova matters because it is not trying to be Starship. That sounds obvious when you put the vehicles side by side, but it is an important point because the phrase fully reusable rocket can make every new system sound like a direct SpaceX rival. Nova is a fully reusable medium-lift launch vehicle. Starship is a super-heavy transportation system built around moving enormous mass to orbit, refilling in space, and eventually supporting missions beyond Earth orbit at a scale no operational rocket currently matches. Stoke is aiming at a very different slice of the market. In reusable mode, Nova is designed to carry roughly 3,000 kilograms to low Earth orbit. If the vehicle is flown expendably, that rises to about 7,000 kilograms. Stoke has also described capability to geostationary transfer orbit and translunar injection, which means Nova is not just a small satellite launcher. It sits in the range where commercial constellations, national security payloads, science missions, and rideshare customers could all become relevant. That is why the better comparison is not Starship. It is closer to the medium-lift competition forming around vehicles like Rocket Lab's Neutron. Both are aimed at customers who need more performance than a small launcher can provide, but do not necessarily need a giant vehicle with Starship's payload bay, mass capacity, or launch infrastructure. This smaller scale gives Stoke one real advantage. Nova can be developed, tested, and iterated with less physical hardware, smaller ground systems, and fewer extreme handling challenges than a super heavy vehicle. A medium-lift reusable rocket can move faster through design loops because each test article, engine set, and ground campaign is less massive and less complex. The limitation is just as clear. Nova cannot match Starship's mass-to-orbit ambitions, and it is not designed to reshape the launch market by brute force payload volume. If Starship succeeds at high flight rate and low cost, it could pressure every smaller reusable vehicle from above. So Nova's case is not that it beats Starship at Starship's game. Its case is that a smaller, fully reusable rocket could serve a market where flexibility, cadence, and right-sized payload capacity matter more than maximum tonnage. And the real surprise is not Nova's size. It is how differently Stoke is trying to bring the second stage back. The first stage is where Nova starts to look familiar, but not because it is a copy of anything already flying. Stoke's booster uses a stainless steel primary structure, and it burns cryogenic liquid methane with liquid oxygen. That combination immediately puts it in the same broad material and propellant family as SpaceX's Starship system, even though Nova is much smaller. Stainless steel can tolerate extreme temperatures. It is relatively inexpensive compared with advanced composites, and it fits well with reusable cryogenic vehicles that have to survive repeated loading, pressurization, flight, and recovery cycles. The visual language is familiar too. Nova's booster shows the kind of clean cylindrical tank architecture, external plumbing logic, and transfer tube style layout that viewers now associate with modern stainless steel reusable rockets. These choices are not cosmetic. They reflect a vehicle built around rapid propellant loading, high structural margins, and a production approach that can improve through repeated hardware builds. At the base of that booster are 7 Zenith engines. Each one is targeting about 100,000 pounds force of thrust. Together, that gives the first stage roughly 317 tons force of thrust at sea level. For a medium-lift rocket, that is a serious engine cluster, large enough to support vertical launch and booster recovery, while still small enough to be tested and manufactured without the scale problems of a super-heavy system. The most important detail is not the number of engines, it is the engine cycle. Zenith is being developed as a full-flow staged combustion methalox engine. In this cycle, both propellants pass through preburners before entering the main combustion chamber, which can improve efficiency, cooling, and turbine life when everything works correctly. That places Zenith in the same elite technical category as SpaceX's Raptor. Very few organizations have ever attempted full-flow stage combustion, and even fewer have pushed it toward operational flight. The reward is a high-performance reusable engine with strong long-term potential. The cost is development difficulty. This is the central bet inside Nova's booster. Stoke is not choosing the simplest engine path to reach orbit. It is choosing a cycle that could make the vehicle more capable and more reusable, but also introduces one of the largest risks before flight. Full-flow engines demand tight control of combustion stability, turbo machinery, seals, ignition behavior, and manufacturing consistency. A small flaw can turn a test stand success into a delay. So while Nova's first stage may look straightforward from the outside, its engine bay carries the hardest question. Can Stoke make 7 advanced full-flow engines reliable enough to fly, land, and fly again? Nova's upper stage is where Stoke stops looking familiar and starts looking almost strange. Instead of using methane and oxygen like the booster, Stoke plans to use liquid hydrogen and liquid oxygen on the second stage. That is a major split in the vehicle's design. Methalox gives the first stage dense propellant, compact tanks, and strong thrust for launch and recovery. Hydrolox gives the upper stage high efficiency, which matters most once the vehicle is already moving fast and fighting less atmosphere. The engine system is called Andromeda 2, and it is easy to describe incorrectly. It is not 24 separate engines mounted around the base. It is one engine system feeding 24 thrust chambers arranged in a ring around the heat shield. That ring-shaped layout is central to the stage's recovery plan, because the propulsion system and the thermal protection system are physically tied together. The most radical feature is the heat shield itself. Stoke is not relying on a field of fragile ceramic tiles like the Space Shuttle or Starship. Its concept uses a regeneratively cooled metallic heat shield. In simple terms, cryogenic propellant flows through channels in the shield, absorbs heat during re-entry, and carries that energy away before the metal structure reaches destructive temperatures. That changes the entire recovery problem. A reusable upper stage has to survive orbital re-entry, where heating can push temperatures to around or above 1,500 degrees Celsius. Traditional heat shields either burn away, which is not reusable in the quick turnaround sense, or use delicate external protection that must be inspected and repaired. Stoke wants the stage's own propellant system to become part of the thermal protection. After surviving re-entry, the stage would relight and land propulsively without parachutes. That is an extremely ambitious profile for an upper stage, because it must handle vacuum engine performance, orbital re-entry heating, restart reliability, guidance, and a final landing burn in one vehicle. This is why Nova's second stage is the heart of Stoke's uniqueness. The booster is advanced, especially with its full-flow methane engines, but the upper stage is the real moonshot, a reusable hydrolox spacecraft with an actively cooled metal heat shield, designed to come back from orbit and land like a miniature rocket stage instead of being thrown away. To make that vehicle real, Stoke needs more than test stands and engine firings. It needs a launch site. And for Nova, that site is one of the most historic pieces of ground at Cape Canaveral. Launch Complex 14 was the Mercury Atlas pad. It is best remembered as the place where John Glenn lifted off aboard Friendship 7 and became the first American to orbit Earth. For decades after the Mercury era, the pad sat largely inactive, with its original role locked in spaceflight history rather than future operations. Stoke is now turning that historic complex into the starting point for a fully reusable rocket. The company's work at Launch Complex 14 has focused on the basic systems that separate a real launch pad from a construction site. A rebuilt flame trench, a water suppression system, propellant tank farms, a launch mount, and the support equipment needed to handle Nova safely before flight. The layout also reflects how Nova is expected to be processed. Stoke is building a horizontal integration facility, meaning the rocket can be assembled and checked out on its side before moving to the pad. That approach can simplify access, reduce time spent working vertically at the launch mount, and support faster turnaround if the vehicle eventually reaches routine operations. One detail makes the refurbishment especially symbolic. Stoke reused crushed concrete from the original Mercury and Atlas era pad in the new construction. That means material from the site that launched early American orbital missions is physically part of a pad being rebuilt for reusable launch. But the practical challenge is now timing. A pad can look close to ready while the rocket is still deep in qualification. Engines must complete testing, structures must be proven, ground systems must be checked, and the full vehicle has to come together without hidden incompatibilities. So Launch Complex 14 is not just a backdrop for Nova. It is a parallel test program. As the infrastructure moves toward readiness and the engines continue their own campaign, Stoke's first launch becomes a race between construction, integration, and propulsion maturity. Nova's first flight is still several major gates away, and the biggest one is propulsion. Stoke's Zenith engines have to finish qualification before they can become flight hardware, which means proving performance, start reliability, shutdown behavior, thermal margins, and repeatability across the operating envelope. A single impressive firing is useful, but qualification is about showing the same engine family can survive the full mission profile with predictable results. After that, the engines have to be integrated with the booster, and that step can expose problems that never appear on a standalone test stand. Feed lines, valves, avionics, pressurization systems, engine controls, and structural loads all have to work as one system. Then the completed vehicle has to ship to Cape Canaveral, enter launch processing, connect to the rebuilt ground systems at launch. Complex 14, and pass rehearsals before anyone commits to lighting it for flight. Stoke is targeting a debut in 2026, which is ambitious, but not impossible. The caveat is that first launches often slip, especially when the vehicle is trying to introduce major reusability from day one. Nova is not just attempting to reach orbit. Its business case depends on recovering both stages and turning that architecture into routine service. That adds technical risk before the first mission and operational risk after it. The funding story also needs careful framing. Stoke has been tied to the National Security Space Launch Lane 1 program, but the $5.6 billion figure is not a guaranteed award to Stoke. It is a shared ceiling across eligible providers. Stoke received eligibility to compete and a $5 million assessment task order, which is valuable, but it is not the same as a multi-billion-dollar contract already in hand. That distinction matters because the launch market is unforgiving. SpaceX is still far ahead in flight rate, reuse experience, and customer confidence. Rocket Lab's Neutron is a more direct medium lift rival, with its own reusability plan and a company that already operates orbital missions. Stoke has a compelling design, strong testing momentum, and a historic pad coming back to life. The real test is whether those pieces can become repeatable flights, because in launch, elegant prototypes only start the conversation. Reliability, cadence, and price decide who stays in it. The balanced verdict is simple. Moses Lake did not change the launch industry overnight, but it showed Stoke is testing real hardware for a serious reusable vehicle. Nova's promise is full recovery, a heat-shielded upper stage, and a focused medium lift roll. If Stoke reaches orbit and brings hardware back, does Nova become SpaceX's most interesting challenger, or does the complexity catch up first? Thank you for watching, and write your take in the comments.